Hi, in today's video I'm going to show you a few ways you can measure the current flowing through your circuit. Current sensing is everywhere, in your LED power supply, smartphone chargers, and even the USB port to your computer. So why not implementing current sensing in your own circuits too? The only thing is that only a small percentage of you watching are actually subscribed. So if you enjoy this kind of electronics content, make sure to subscribe. Let's start from the basics, a simple voltage divider. We know that since R1 and R2 are in series, the current through them must be the same. Just use Ohm's law. Now if we want to calculate the voltage drop on R2, we can simply multiply the resistance times the current. And if we lower R1, more current will flow and more voltage drop we have. Now we can get rid of R1 and replace it with our circuit. R2 will always follow Ohm's law no matter what. So we will use R2 to calculate the current flowing through our circuit. R2 is often called sense resistor or shunt resistor, and to sense the voltage across it I will use the analog pin of an Arduino Nano. So the final circuit looks like this. We have the first resistor, the potentiometer, the LED, and our sense resistor. Now let me turn on the multimeter and let's see how close the Arduino readings are to my multimeter. As you can see, the readings are pretty bad, mainly because the voltage is only 20 millivolt, which is really low for an Arduino. You can see the values are really jumping around. So let's see if this gets better by increasing the current. Okay, that should be good. Again, we have some discrepancies between the Arduino readings and the multimeter readings. One way to improve our readings is to use an operational amplifier. In this case, I used a gain of 20. And the readings were surprisingly good, both had low value and higher values of current. But if you want a more integrated IC, you may want to try a current sense amplifier, which basically is an operational amplifier with embedded matched resistors. For this particular series, you can find 1-channel version, 2-channel version, and 4-channel version. This is what the circuit looks like with an NINA 180. Again, the readings were pretty good, and I was satisfied with the overall result. In those first three methods, we relied on the 10-bit Arduino ADC, but another thing you may want to try is sensing the current with an external ADC, like this I2C 16-bit ADC. In particular, I'm using the 4-channel version. It was the only I had. This is the circuit for our application if you want single-ended readings, or you can also use this one if you want differential readings. It's better for noise suppression. Okay guys, let's try this ADC here. We're gonna, as always, compare it with the multimeter. Let me plug this USB in and let's see the readings. There we go. Pretty bang on. So my ADC matches my multimeter. Now let's try and increase the current and stop to a random value maybe. So there we go. The values are really close to each other. Let's do it one more time so you can see it was not a fluke. Anyway, it is still pretty accurate. As last, we have power monitors. For example, the INA226 is a 16-bit power monitor with I2C interface. Power monitors offer both voltage reading and current reading. You can see here they mention the term high-side shunt and low-side shunt. And basically, this is low-side sensing and this is high-side sensing. Anyway, this time I want to show you a real implementation using my PPS trigger board. Okay, at the top we have the INA226 voltage and current readings, whereas at the bottom we have the set voltage and current. I'm increasing the current with an electronic load, sorry if it is out of camera, and as soon as we go over the target current, it goes in overload mode and it basically shuts down the output. How this works? Well, basically the INA226 senses the voltage drop across this resistor here, that is our shunt resistor, and talks to the MCU. If the voltage drop is across a certain value that I can set with the encoder, the MCU talks to the PD controller to shut down the output voltage, and it does this by controlling those two MOSFETs here. Now, some of you may even notice those two PCBs have something in common. In fact, they were both manufactured by PCBWay that sponsored this video. If you want really good looking PCB, I highly suggest to check PCBWay.com using the link in the description. They can also assemble PCBs for you or offer 3D printing and CNC machining, with tons of material to choose with. Just check PCBWay.com, link in the description. Let's talk a bit about how to size our shunt resistor. Let's say we want to use the ENA226 to sense the current through our shunt resistor. The first thing we want to do is to check the maximum allowable voltage drop. In this case, we are limited by the ENA226 with a maximum value of 81.92 millivolt. So to round up, we will say 80 millivolt. Now let's say the maximum current in our circuit is 5 amps. So we have to choose a shunt resistor that at 5 amp gives us 80 millivolt of voltage drop. That is a 16 milliohm resistor. Now 16 milliohm is a strange value, so we will go with 15. So at 5 amp we have a 75 millivolt of voltage drop. Now we want to calculate the power loss, that is 375 milliwatts. So if you ask me, I will either choose a 750 milliwatt resistor or a 1 watt one. When implementing the circuit on a PCB, you should separate the high current trace from the sense traces. So this is a good layout, whereas this is a bad layout. There are also 4 terminal resistors like this one that can help in the PCB design. Anyway, I almost forgot of all effect current sensor. Those current sensors do not need a resistor as they rely on the magnetic field to sense the current, and they output the voltage proportional to the current flowing through them. Mine outputs 40 mV every amp of current. But of course they are also sensitive to unwanted magnetic field. Okay guys, that's all. Thank you for watching, subscribe and see you next time. Bye.